We've already explored Young's double slit experiment, in which we take a source and keep it behind two holes, and that produces this nice pattern of alternating dark and bright spots, and that happens due to constructive and destructive interference. In this video, we want to figure out an expression for the distance between two consecutive bright spots. We want to figure out what is the expression for this distance. Why? Well, one is because this is in our syllabus, but more importantly, we will see by figuring out this expression how Thomas Young was able to find the wavelength of light. That's right, by using a piece of cardboard, candle, and a screen, he was able to figure out the wavelength of light, and we'll understand exactly how he did that. So let's begin. To start with, this distance is often called beta, and the name is fringe width. That's the name we give to it, fringe width. And the name was confusing for me because I thought we were calculating the width of something, but we are not. See, over here, what we find is that the brightness is maximum, then it becomes smaller and smaller, then it becomes minimum, then the brightness increases and becomes maximum, and then minimum and maximum, minimum. So fringe width is the distance between two consecutive brightest spots, where the brightnesses are the maximum, or distance between two consecutive darkest spots, where the brightness is 0. So it's not the width of anything, it's the distance between two consecutive brightest spots or two consecutive darkest spots. So how do we figure this out? Well, there are a couple of ways to do that. The way I like to do it is this way. See, when these rays interfere over here, these are the two rays of light interfering over here, I know that they're undergoing constructive interference over here, right? All I need to figure out is what is this angle? This angle. If I can figure out what this angle is, then I can figure out this distance by using geometry. See, I know what this distance is experimentally. The distance between the screen and the slits, we can just call that as capital D. And we also know what this distance is. Distance between the slits, we can call that as small d. So if I figure out what this angle is at which this constructive interference is happening, then from geometry, I can figure out what this distance is going to be. So the next question is, how do I figure out this angle, the angle at which constructive interference is happening? Well, for that, we'll go back and ask ourselves, what is the condition for constructive interference? And this is something we have seen before. In our previous videos, we've seen for constructive interference, the path difference between the two interfering waves, that should equal an integral multiple of the wavelength lambda. What is this equation saying? Well, over here, you can kind of see that this one is traveling slightly more distance compared to this wave, right? Because this is slightly farther away from this source or this slit. And so that extra distance is called the path difference. If that equals an integral multiple of a wavelength, then we'll always find constructive interference. Now, if you're wondering why this is true or where this comes from, we've talked about this in great detail in our previous video. So feel free to go back and check that out. So when m equals 0, we get the path difference to be 0, and that happens right at the center. So we get the central bright spot. When m equals 1, we get the first constructive interference here or here. When m equals 2, we get the second. Now, since we are interested in the first constructive interference, we'll put m equals 1. So we're writing first construction. That's what I want. And so we can say for us, m equals 1. So over here, I know the path difference is exactly equal to 1 lambda. But from that, how do I figure out what this angle is going to be? Well, the path difference does depend on the angle. Think about it. If the angle was 0, then we're going to get 0 path difference. They're going to travel exactly the same path. But as the angle increases, the lower wave has to travel more distance compared to the top wave to catch up and meet with it. So clearly, as the angle increases, the path difference will increase. So there is a relationship between them. But what exactly is that? How do we figure that relationship out? Now, this is also something we've done before. What we did, just to recap, is we zoomed in over here. Let me show you the zoomed in version of that. And now to calculate the extra path traveled by this wave compared to this wave, we said, let's drop a perpendicular from here to here. Why? Why did we do that? Well, we can now say, hey, the distance from here all the way to the screen and the distance from here all the way to the screen is the same. Because if you think about it, if you drop a perpendicular here, this becomes a giant isosceles triangle. Almost with these two sides 90 degrees, these two angles 90 degrees, and this angle is almost 0. You have to imagine it that way. And that means if these two distances are the same, this part, this is the extra distance traveled. And from this geometry, we can figure out what that is because I know what this length is. This is D. I know this is D. And if this angle is theta, you can find the angle inside this triangle and you can use trigonometry. So great idea to pause and see if you can recollect what we did in the previous video or just use this geometry to figure out what this distance is going to be. Can you pause and quickly try and figure that out? All right, let me zoom in so we can see better. All right. So if this angle is theta, the first thing we see is this angle should also be theta. Why? Because this whole angle is 90, right? So if this is theta, this should be 90 minus theta. This is 90, so this should be theta as well. And now I know this is the hypotenuse, which is D, and this is the opposite side. So to figure out the opposite side, I can use sine. And if you do that, you will now get the opposite side to be D sine theta. And that is our path difference. Let me zoom out. And so we can say the path difference is D sine theta. And so for constructive interference, for the first construction, that should equal lambda. And again, if you need more clarity, feel free to check back our previous videos where we've discussed this in more detail. But now comes the question, from here, how do I figure out what theta is? Well, remember, theta is incredibly small. So when theta is small, and it usually happens to be a few degrees, 1 or 2 degrees, then we can do another assumption and we can simplify this. And from that, we can figure out what theta is going to be. And then we can use a little bit of geometry to figure out what beta is going to be. So I want you to pause the video at this moment and see if you can do the rest of this yourself. It's important to try. It's okay if you go wrong, but please try this first yourself. All right. Now, because theta is small, the assumption we can do is sine theta equals theta. For small angles, sine theta is the same value as theta when you're dealing with radians. So we can just say this is D times theta. That equals lambda. And from this, we can immediately get what theta is going to be. Theta is going to be lambda divided by D. So we found the angle that is subtended by these two bright spots over here. Now we found out the angle, but how do I calculate this distance? You can again use trigonometry, or you can, again, because the angle is very small, we can use the arc angle formula. We can say that, hey, this distance is almost the same as this distance. And so this length is very small, so we can assume this to be an arc. And so for the arc angle formula, I know S equals R theta. Oops, sorry, what was that? Okay, S equals R theta. So our arc is the beta over here, beta. The radius is the capital D times theta. And therefore, if I substitute, I get beta to be, I'll first substitute theta. That'll be lambda divided by D times capital D. And if you had used trigonometry, you would have gotten the same answer. You could have used trigonometry and say, I can use tan theta, and then tan theta becomes the same thing as theta because the angle is small. You would get exactly the same result. You can try that. But anyways, we have found the expression for fringe width. Now, before we talk about how Thomas Young calculated the wavelength, one question I have is, we found the angle between these two bright spots, or the distance between these two bright spots. Would the answer be the same for distance between these two bright spots? Would we get the same answer? Well, it looks like that, but can we prove it? Well, yeah, let's quickly try and do it. Again, feel free to see if you can prove it yourself. But now we'll consider the interference between, for the second constructive interference. Let me use same yellow. Second constructive interference here. And to calculate the angle, the distance between these two bright spots, I have to again calculate what this angle is going to be. And again, why don't you think about that? You can do it very quickly over here. All right. So for the second constructive interference, my M is going to be 2. So I'll get this to be 2 lambda. So this will be 2. And this angle, this total angle is going to be 2 lambda by D. But since this angle is lambda by D, total angle is 2 lambda by D, that means this angle is also lambda by D. So what we see is this angle is exactly the same as this angle. And therefore, this distance will turn out to be exactly the same as this distance. Again, because we are assuming theta to be very small. Of course, if I go very far away, very high, then eventually theta becomes big enough, and then I can't do any of these assumptions, and then it will fail. But as long as the theta angles are very small, we can use this assumption. And so distance between any two consecutive bright spots or dark spots, and you can prove this yourself. You take any two dark spots also, you will find the distance to be the same, lambda d by small d. So now let's come to the fun part. See, Thomas Young also did this calculation and he knew that beta is going to be lambda d by small d. Now in his experiment, he experimentally found out using a ruler and maybe a microscope, because this distance will be very small, what was the distance between two consecutive bright spots. So he experimentally calculated this. And in his experiment, he knew what the value of capital D and the value of small d was. And so by plugging in, he was able to figure out the wavelength of light, which I feel is mind blowing, because, you know, if someone told me that you can use a candlelight, a cardboard, a screen, and a microscope to find the wavelength of light, I wouldn't be able to believe that. And that's why this is one of the most important experiments in history. Okay, finally, let's look at what this expression is telling us. It's telling us that if the lambda is high, if the wavelength of light is larger, then beta will be larger. So if you use red light, which has a larger wavelength, you would expect the beta to be larger. The bright spots will be farther apart. If the distance increases, if the distance between the source and the slit and the screen increases, then beta becomes larger, which kind of makes sense, right? The angle does not depend on that, but as you go farther and farther away, you can see they are diverging away. And as a result, you can see the bright spots go farther and farther away. Finally, what we see is, you tell me, what do you think will happen if I bring the slits closer to each other? Do the bright spots will also come closer, or do you think the spots will go farther away? What do you think? Well, from the equation, you can see if the slits come closer to each other, the beta value increases because in the denominator. So the bright spots will end up going farther and farther from each other, and we'll be able to see a better interference pattern. And this is important. So to actually see a nice interference pattern, you have to have the two slits close to each other. If the slits are very far away, if the distance is very large, if let's say a few centimeters or meters, then beta value will be so small, you can hardly notice any interference. And that's why if you have, say, two windows through which sunlight is coming in, the windows are too far, the distance is too far to see any interference on your wall.